Hello everyone and welcome back to this next lecture in the Machines lecture series. I took a short break during summer and I'm back now. So this is where we had left off in the previous week, where we were writing or rather drawing the equivalent circuit of a single phase induction motor, and we had written the circuit for the stator and we had written the circuit for the rotor. The difference in the last lecture was that we had introduced this concept of a slip, that is this value S. So this value S that you see here is called the slip. And in this lecture, in the next few lectures, we'll start talking about what is this slip and why does it show up here in this rotor circuit. So as usual, before I start this lecture, a little bit of brief background that if you're interested in these kind of online videos, but you would like something a little more comprehensive, I do have full-length online courses. Now, the latest change has been that now my courses are going to be hosted on this site called Decibel Labs. This is another education technology platform, or rather education platform specifically geared towards engineering technology. So besides my courses also being on Udemy, they will also be on Decibel Labs. The specific link for all my courses is on this page, and I'll be providing the link in the description for this video. So if you're interested in these courses, do check out the description of this video. And as you can see, all my courses which are on Udemy are also hosted on this website as well. So if you're interested, please do check it out. Just a quick background that the very first course, this is the beginner level course, that is simulating power electronic circuits using Python. And in this I talk about how you can simulate circuits, or rather power electronic circuits, using Python and Python power electronics. So this is the first beginner level course that I would recommend you to take if you want to start this entire journey into simulating circuits with Python. The next course is again another basic course, which is Basics of Digital Signal Processing for Power Engineers, and this talks about the basics of how you can analyze and design controllers, or rather signal filters such as notch filter and low pass filters, using Python packages such as the SciPy package and the signal package within SciPy. The next course is, which I would say in the advanced category, is Simulation of Magnetics for Power Electronics using Python. In this course, I assume that you already know how to simulate circuits with Python power electronics, and I talk about how you can simulate magnetic components like inductors, coupled inductors, and transformers using Python power electronics. And the latest and the most advanced course I have is Control Analysis with Python for Grid Connected Converters. And in this I talk about how you can analyze and implement controllers using the Python control package specifically designed for power electronic applications. So I take the example of a single phase grid connected converter with which I try out different controllers, and I try to implement and analyze them and figure out how to actually describe the process of how you would implement a controller for any given purpose. So as before, the link for this courses is provided in the description for this video. If you're interested, please do check it out. With this, I'll get back to the lecture. So this is where we were, and as I said, the difference was that we had introduced this concept of a slip. Now in this lecture, I'll get started about why this slip appears. So as we had already said, in any case, you have a single phase induction motor which is energized by a single phase supply voltage. So this can be a 240 volts 50 hertz supply depending on where I am. For example, I'm in Germany. Any single phase supply is usually 240 volts 50 hertz. If you're in North America like US or Canada, it's probably 120 volts to 60 hertz, and there are a few other variations, right? So when you do energize a single phase induction motor with a single phase supply, right, this will result in a current flowing in the stator. So this is the stator circuit. Now this stator circuit is going to be seeing a current flowing through it which is at the same frequency as that of the supply. So for example, if you have a 50 hertz supply, you will have a 50 hertz current flowing through it. Now because of this, and let me go over to the actual circuit of an induction motor. So this is the induction motor. So you see that this is our stator winding. Now as I said before, we are not talking about the auxiliary winding yet, so we have a single main winding. When the current flows through this stator winding, it is going to produce a flux in the air gap, right? So this is the stator, this is the rotor, it's a squirrel cage rotor. So when we pass a current, or when we supply a voltage to the stator winding, it's going to result in a current flowing through the stator. That's going to produce a flux in the air gap. That is a gap between the rotor and the stator, right? Now, this is fairly obvious. Why? Because whenever a current passes through any coil, it's going to produce a magnetic field. Now, this magnetic field is going to be changing with respect to time. And that changing magnetic flux is going to induce an EMF in this rotor, right? That's what's going to happen. So this is going to result in an induced EMF in the stator and also an induced EMF in the rotor. Because remember, when any changing magnetic flux is associated with a coil, that could be a stator coil or a rotor coil or a rotor cage winding, is going to result in an induced EMF. The stator is always stationary. Therefore, the induced EMF in the stator is going to have the same frequency as that of the supply. But the rotor is going to eventually start moving, right? Initially, the rotor is at rest, right? When the rotor is at rest, the induced EMF will have the same frequency as that of the stator. But as the rotor starts rotating, this induced EMF will now have a different frequency. Now, the reason for this is a little different. So let me talk about this. So, as I've already said, the supply frequency can be called omega s. So this supply frequency, right? Now, we can actually write it instead of omega s as ns. Ns is the synchronous speed. Alright. Now, what is the synchronous speed? As I already said, when we have any frequency applied to this system, there will be a synchronous speed corresponding to it. Now, assume for now that it's a simple two-pole motor, which means there is a single north pole and a single south pole. In that case, we will have a synchronous speed of 160 F, that is 60 times the frequency. And this has usually a unit of RPM, or revolutions per minute. Right? If, however, we take the general case of having multiple poles, right, then in that case, this is going to be 120 F divided by P. And here, P is the number of poles. Right? So you could have a simple two-pole motor, which is single north pole and a south pole. You could have 4 poles, which means 2 north poles, 2 south poles, and you could have many more, right? Of course, naturally, P will always be a even number, because you always have to have a north pole and a south pole. You can't just have a north pole or a south pole. So this is our synchronous speed, right? So whatever you choose, for example, if I have a simple two-pole motor, my frequency, and let's say I have a frequency of 50 Hertz, this will result in a synchronous speed, quite obviously, of 3000 RPM. 3000 revolutions per minute. This is the synchronous speed. Now, in an induction motor, let's go back here. In an induction motor, the way it works is the air gap, the flux in the air gap induces an EMF in the rotor. As we already know, the induced EMF is such so as to oppose the cause which produces it. Right? Now, what this means is the cause which produces it is this changing magnetic flux. And therefore, this rotor, or rather the induced EMF, has to be such that it opposes this changing magnetic flux. Now, the way it does is that the rotor begins to rotate. The rotor begins to rotate such that by rotating, the induced, or rather the flux produced by this rotor will be exactly the same or opposing this magnetic flux. That is how it works. But in an induction motor, it will never ever achieve the synchronous speed, because if it achieves the synchronous speed, the induced EMF becomes 0. Right? Now, this may be a little complex to understand, and the simulations will help. But what is important to understand is that if the induction motor, the rotor is rotating at some speed, and let me go back here, let me say that the rotor speed is what is called Nr. If the rotor is rotating at some speed Nr, it is important to note that this Nr will never ever be equal to Ns. Because if the rotor speed is equal to the stator speed, there will be no induced EMF in the rotor, and therefore the rotor has no need to rotate anymore. So therefore, the stable steady state will always be such that the rotor speed is not equal to the stator speed. And typically in the case of a motor, the rotor speed will be less than that of the synchronous speed. So now that we talk about it, we now say that we have two different speeds in the system, right? Which means the rotor, because it is rotating at this speed Nr, the frequency will no longer be the same as that of the stator. The stator is at 50 Hz. The rotor is now no longer at 50 Hz because why? It is rotating at a certain speed. The reason now is it becomes a difference of speeds, right? This now becomes almost like a moving reference frame. Because our rotor is moving at a certain speed, the actual frequency within this circuit is the difference between these two speeds. And this is defined by the slip. The slip, or S, is defined as Ns minus Nr divided by Ns, right? So this means that we are taking the difference between the synchronous speed and the rotor speed and dividing it by the synchronous speed. The result is this is a kind of a ratio. So the closer your rotor speed gets to the synchronous speed, the closer this slip will get to 0. And quite obviously, when this rotor speed is 0 initially, this slip is going to be 1. So this slip is a value between 0 and 1. 0 is when the rotor speed is equal to the synchronous speed, and as we said, this never happens. And 1 is when the rotor speed is 0, which means the rotor is at rest. This does happen because when we switch on the motor, it is initially at rest. So this means that when the rotor is rotating at some speed Nr, the value of the slip is going to be something close to 1, something close to 0. Now, with this speed S, we have to take into account that if we had induced EMF in the stator equal to ES, and this induced EMF was producing an induced EMF in the rotor of ER at rest, when the rotor is rotating, the induced EMF will be further reduced by this slip S, right? This has to take into account that now this rotor is close to the speed of the stator, or rather close to the synchronous speed. This difference has to be taken into account in addition to any winding ratio between the stator and the rotor. Moreover, since there is a new frequency in the rotor, because of this difference between the synchronous speed and the rotor speed, the inductance is also going to be decreased by the same amount, right? Why? Because if you have a low frequency circuit, the inductance in this low frequency circuit will also decrease. So therefore, this inductance also takes this ratio of SR, right? And this is fairly normal. Whenever you have an induced, this is like Laplace transform almost. If you have a new frequency, the induced EMF, or rather the inductance, will be decreased by that frequency. The rotor resistance will not change, right? Because the resistance is independent of the frequency. So this is where we get this concept of this rotor frequency entering, or rather the rotor speed enters the rotor equivalent circuit. So with this, I will end this lecture, because in this lecture I wanted to talk about how this speed S appears into LR. And the reason for that is because we have to take into account that once the rotor starts rotating, the equivalent frequency within the rotor circuit is no longer 50 Hz, but is the difference between this synchronous speed and the rotor speed and this ratio which is defined as a slip. So as we said before, S is called a slip, right? The slip is the difference, or rather a kind of a ratio of the difference between the synchronous speed and the actual rotor speed. So this, as I said, might be a little confusing. It may become a little clearer once we actually start simulating it. But a few more lectures are necessary in order to be able to create this equivalent circuit of the rotor with which we can start simulating. For now, all you have to understand is that once the rotor starts rotating, since we are talking about a rotating machine rather than a transformer, the induced EMF is not just dependent upon the turns ratio. If this was a transformer, the induced EMF in the rotor, or rather the secondary, would be purely dependent on the ratio of the windings between the stator and the primary and the secondary, right? If this was instead the equivalent circuit, not of an induction motor but a transformer, the only thing that matters is the turns ratio between the primary and the secondary. But now this is a rotor, this is a machine. So not only do we take into account the turns ratio between the stator and the rotor, but also the slip between the synchronous speed and the rotor speed. This is what needs to be taken into account. So as before, if you have any doubts, please do post either in the comments or send me an email or message me on social media. In the next week, I'll talk about another simplification that is usually done with this rotor circuit, and then it is brought into the main circuit so that we can start analyzing them. So, thank you so much for watching and see you soon. Goodbye for now.